Hi guys, so now we continue on the second part of chapter 2 to define a KC in a PBR. Okay, now we can calculate KC using two methods which are Thorne and Kramers or using JD-Coburn factor. So you need to choose either one. So basically the decision is made based on these factors. Okay, if let's say your phi, which is void fraction of pet bed, okay, is in between 0.25 to 0.5, okay, and then your Schmidt number is in between 1 to 4,000, and finally your Reynolds number prime between 40 to 4,000. So you can use Thorne and Kramers to calculate your KC. And then if the value is not within the range of these three parameters, which are the phi, Reynolds number prime, and also Schmidt, so you have to use Coburn J factor. Okay, so let's go have a look on how to calculate KC using Thorne and Kramers first. Okay, so if you look into the equation, so you can calculate Kc as stated in the equation in the slide. So if you refer to your textbook, this equation is actually equation 1166 in your textbook. Okay, okay. Bear in mind, okay, the dp used in this equation 1166 is actually applied for the catalyst shape for spherical. Okay, if let's say your catalyst shape is not spherical, maybe it's cylinder or pyramid. Okay, so you need to apply the formula for dp, which is 6 over pi times volume of pellet to the power of 1/3. Then only you can use dp in the equation, right? And then gamma, the shape factor, for spherical is actually equals to 1. But if the shape of the catalyst is not spherical, so you need to follow this formula, which is external surface area divided by pi dp square. Okay, and then you need to calculate the Reynolds number prime first, and then Sherwood prime. Okay, so that's for Thorne and Kramers. So now if you want to calculate Kc using JD Coburn factor or Coburn J factor, so in order for you to solve for the Kc, so you need to calculate the JD value first. So JD is actually equals to Schmidt over Schmidt 1 to the power of 1/3 times Reynolds number. So if you look in your textbook, this equation is actually equation 11.68. Okay, so but then before you solve that, you need to solve for JD. Okay, so JD, you can solve JD by having equation 1169 in your textbook. But solve first for the Reynolds number, then insert back into equation 1169. Okay, so once you get the value of JD, now you can calculate your Sherwood number using equation 1168 to get the Sherwood number. So finally, when you get the Sherwood number, then only you can calculate Kc, which is Kc equals to DAB over dP times Sherwood. So this actually, the value of Kc, the formula of Kc used in Coburn J factor is similar with the one that we use in calculation of in single particle. Okay. So now we take a look at example in the book. Okay. So a few keywords that I have highlight here. So you can see it's a mixture of hydrogen and helium. So this will affect your mole fraction. And then it's passed over a packed bed of cylindrical particles. So the shape of catalyst is cylinder, and given to you the diameter and also the length of the catalyst. Okay, and also the gas velocity, which is U, is 150, and at temperature at 450. Given to you also the kinematic viscosity at temperature of 550. Okay, so this is the most important keywords. Externally mass transfer limited. So you will directly use equation that related to external mass transfer. And then given to you the length of the reactor, the question required you to calculate the x. Okay, so bear in mind, okay, if you look at the temperature of the reaction is about 450, but the data given DAB is at 298. So you need to later on you need to convert this DAB in at temperature of 450. And also given to you additional information, the back porosity, which is 40% or equals to 0.4. Okay, so if we put into a figure and transfer the question, it will be something like this with a length of 0.05. So they required for you to calculate the x. Okay, this is from the earlier equation when we derived just now. Okay, so ln 1 over 1 minus x equals to kCAC over u times L. So it's from equation 1164 in your textbook. Okay, first let's have a look on solving Kc if we follow the Thun and Kramers correlation. Okay, so since from the question just now we know that the catalyst shape is not sphere, so we calculate dp. Okay, so and then after that we calculate AC. So where AC, the formula given is actually stated in your book. It's actually equation E11-3.3. I've also has specify this AC equation in our previous lecture note, right? So from here we can see the dP calculated is 3.61 10 to the power of minus 3, and AC is 998 meters square per meter cube. Okay, now before we can calculate your mass transfer coefficient, which is Kc, we need to solve first for the gamma, Reynolds number, Schmidt, and also DAB. Right, so as indicated by the equation, you can solve for gamma and also for Reynolds number. So Reynolds number prime is only applied for Thun and Kramers, not in Jacobian factor, right? Then we go to, before we can calculate the Schmidt number, so we need the DAB. So bear in mind just now given DAB at 298 Kelvin. So you need to calculate a new value of DAB at 450 K. That is the reaction temperature, and this one you can calculate the new value of DAB by using formula in table 11.2 in your textbook, right? Okay, so once you get the DAB, so now you can calculate Schmidt. Okay, so that is how to solve for those Reynolds number, gamma, Reynolds number prime, and Schmidt. Okay, so now I want to show you. Okay, earlier I already told you that in order to choose either Thun and Kramers or to use Jacobian factor for Kc is depends on the value of phi, Reynolds number prime, and also Schmidt. So let's see here. Okay, if we can have a look, the phi provided in the question is actually 0.4, which is in between the value of required by the Thun and Kramers. And then let's have a look on Reynolds number prime, where we can see that from the calculation. Okay, so we substitute the Reynolds number prime and Schmidt that we obtained just now into the equation. Okay, equation 1165. We get the value of Sherwood prime, and then we insert all this value in equation 1166 to finally determine the value of Kc. right? So now the Kc from this calculation is 6.15. Then we apply this Kc into equation 1164 to get the conversion value at rectal length of 0.05 meter. So the final conversion using Kc determined from Thorne and Kramers is actually 0.87%. Now we consider to calculate Kc by using Coburn-JD factor. Okay, so before we can use equation 1168 and 1169 to determine the JD. So we need to, since this is the shape of the catalyst again is not a spherical, so we need to calculate the A and the dP for the catalyst, right? So dP can be calculated using the formula stated in page 785. This is under J Coburn factor. So you can find it from page 785 in your textbook, where dP is actually equals to AP over pi square root, right? Okay, so you get the value of dP, and then insert the value for dP into AC. So now you calculate the Reynolds number for JD Coburn factor is equals to almost 12,000, which is this is slightly different value with the Reynolds number calculate using Thorne and Kramers. Okay, so later if you have already calculated the value of Reynolds number, so you insert into the equation to solve for JD. So JD from this equation will get somewhere 0.25. Then this JD value you insert into equation 1168 to get the value of Sherwood number. Okay. So here, once you get the value of Sherwood number, okay, which is equals to 212, and then you can determine your Kc, okay, by using the same formula that we have already learned in the first part of chapter 2, okay. So the value of Kc is equals to 7.63 meter per second, which is slightly different from Kc calculated using Thorne and Kramers. Then again, once you have already find the Kc, determine the Kc value, so you insert into the design equation of the PBR as stated in equation 1164. You get the value of X is about 0.9%, which is slightly higher than the one determined by Kc using Thorne and Kramers. So for example 11.4 and 11.5 in your textbook page 789 to 792, you will solve the example by using this correlation for Kc, where Kc is directly proportionate to velocity and also inversely proportionate to particle size. We have discussed this actually during the early chapter on mass transfer in single particle. So I've completed chapter 2. So see you guys in another chapter, chapter 3, internal diffusion. Bye.